In this video, we will continue discussion on unimolecular elimination reactions. For more videos, you can visit us at educationstudio.in. Let us see the energy profile of E1 mechanism. This is reactant molecule, reactant of the rate determining step. These are the products of rate determining step where we will be getting carbocation and L-. The energy of these intermediates formed in RDS will be higher because the bond cleavage will be endothermic process. This is transition state where the carbon leaving group bond is partially broken. The energy of transition state is higher than the reactant as well as product of RDS. This is the energy diagram. This is activation energy of the rate determining step. Suppose this was in a less polar solvent. Now we are supposed to understand what will happen if solvent polarity is increased. Now the products of the RDS were ionic. So when we increase the polarity of the solvent, those polar solvent will attract these ionic products of RDS and will stabilize them. Their energy will be decreased to a very significant amount. So large increase in solvation when solvent polarity is increased, therefore the energy of these ionic products of RDS will decrease a lot. This is partially polarized transition state. When solvent polarity is increased, there will be only slight increase in solvation, and therefore the energy of this partially polarized transition state will decrease to a less extent, slight extent. This is neutral species, neutral reactant of the RDS. So when solvent polarity will be increased, there will be hardly any change in the solvation of this neutral species. So no change in solvation. This is the energy diagram for energy profile for the reaction in more polar solvent. So this is more polar solvent where activation energy will be decreased. Therefore, because of decrease in activation energy, rate of E1 reaction increases a lot when solvent polarity is increased. So therefore, what we can conclude is, when solvent polarity is increased, increase in solvation of neutral reactant RL is negligible. Increase in solvation of partially charged transition state is small, whereas increase in solvation of charged intermediates is very large. Therefore, when solvent polarity is increased, activation energy is decreased and rate of rate determining step and hence rate of E1 reaction in totality will increase. Next point. As carbocation, which has 6 valence electrons and a vacant orbital, is formed during RDS, rearrangements are possible before the loss of H+ from the resultant carbocation. Next point is, because proton has to be removed from adjacent atom of a carbocation, which is in fact an easy process, therefore a weak base like H2O, ROH, etc. can also act as base. A strong base is not required for E1 reaction. Moreover, it must be remembered that increase in basic strength of the base or its concentration will not increase the rate of E1 reaction because the base is involved after the rate determining step and the rate of the reaction is equal to rate constant K and the concentration of RL only. 6th point. Because carbocation is planar, so removal of H+ from both the sides of the plane of the carbocation is equally favored. Therefore, we can say that E1 reaction can be anti-elimination, which means removal of two groups from opposite sides, and it can be syn elimination also, which means removal of two groups from same side. 7th point is, If removal of a proton from two or more different adjacent atoms is possible, removal of proton occurs almost exclusively from more electronegative atom. See this molecule. H plus can be removed from the oxygen, H plus can be removed from the carbon, H plus can be removed from this carbon also. So H plus will be removed almost exclusively from the oxygen. And once this H plus is removed, that oxygen and carbon will form the pi bond. So when H plus is removed from this more electronegative atom, we will get this product where carbon and oxygen will form pi bond. But if adjacent atoms are same, more stable, which is actually more substituted alkene, that product is major product. See this molecule. Here H plus can be removed from either the carbon on the left side, or H plus can also be removed from the carbon of the right side. So when H plus is removed from the carbon on the left side, we will get this alkene. This is 2-butene actually. If we remove H plus from the carbon of the right side, those electrons will form pi bond. After the removal of H plus, we will get 1-butene. Out of these two products, upper product, which is 2-butene, that is more stable because of more number of hyperconjugation. More substituted alkene is more stable. So that product which is more stable will be major product. Eighth point is that unimolecular nucleophilic substitution will be the competing reaction, because carbocation, which is formed in the rate determining step after the removal of L- can combine with any nucleophile. We will discuss SN1 mechanism later on. There are some examples of even elimination, which are acid catalyzed dehydration of most secondary and tertiary alcohols. This is 2-butanol. When H plus is added to it, lone pair of the oxygen will form a bond with H plus. We will get this protonated molecule where O will become positively charged. From this molecule, water will be removed, which is a very good leaving group. When this water is removed, along with electrons of the bond, we will get a carbocation, and this step is rate determining step. So this is the carbocation formed during the rate determining step. This carbocation can then lose H plus either from the carbon of the left side or from the carbon on the right side. Once it loses H plus from the carbon of the left side, we will get 2-butene. But when it loses H plus from the carbon on the right side, it will give us 1-butene. Out of these two products, 2-butene is having 6 hyperconjugation effects, while 1-butene will be having only 2 hyperconjugation effects. Therefore, 2-butene is more stable product, and that will be major product. This is called Saytzeff elimination or Saytzeff elimination sometimes, where more substituted alkene is more stable, and that is the major product. The lower product is less stable, and that will be the minor product of the reaction.